So there's something to see with these, with both of these, that actually makes them not as terrible to deal with as you might think they were. But it does require some insight. So let's look at the surface area one first, but we will definitely look at the volume one as well. So here's the surface area one I have, and we'll set it up real quick here. So find the minimum surface area of an open top box with volume. So open, they just say open, I usually say open top box, I guess it's with volume equal to, I think, 216 whatever's cubic feet, cubic inches. We don't really care about the units. And so that's what we're in. So we draw our box. We label the sides X, Y, and Z. And then we say, okay, the surface area is, let's see, it's the bottom side, which is XY, plus the front side and the back side, which is an XZ plus another XZ, so 2 XZs. And then the left side and the right side, which is a YZ, so 2 YZ. And of course, we only have the ability to optimize functions of 2 variables. So we need a constraint to get rid of one of those variables. So the constraint is the volume, which is X, Y, Z is equal to 216. We're going to isolate usually Z, although really you could pick any variable, but I would isolate Z because it's the one that's kind of symmetric here. And also because we're used to working with X and Y. So Z is 216 divided by XY, and we throw that in for Z in each of those spots there. So then our surface area equation becomes XY plus 2X times 216 over, sorry, I'm going for that number to be 108. Apologies. It's not a huge deal, but it will make our answer nicer at the end. Let's make that 108. Sorry about that. The way we're picking this number, by the way, so if you notice all the numbers in these problems, I know you all have different numbers. All those numbers are half of a cubic number. So some of you had like 62.5, which is half of 125, which is 5 cubed. The one I'm looking at here is 364.5, which is half of 729, which is 9 cubed. So that's not on accident. There's a reason why that's the choice. So 108 is half of 216, which is 16. So let's see. So yeah, that's going to be. So we're going to have 108 over XY plus 2Y times 108 over XY. And I'm going to cancel an X here and an X here, and a Y here and a Y here. So I'm going to write that my surface area is XY plus 2 times 108 is 216, Y to the negative first, plus 216, X to the negative first. So all that's well and good, and that's not an insignificant part of this, right? Setting it up and getting the surface area equation in terms of 2 variables is a not insignificant part. But now we have to find the critical points by setting the partial equal to 0, or the gradient equal to 0, which is the same as setting the partial equal to 0. So let's write the gradient. I'm going to write on the other side. So my surface area again was XY plus 216, Y to the negative first plus 216, X to the negative first. Something worth noting, and I said this last time, I'm going to say it this time, I'll probably say it next time. If you have an equation that you're trying to maximize or minimize, and you notice that if you switched X's and Y's, meaning all the Y's became X's, all the X's became Y's, if you switch X and Y and the equation is still the same, that means that your answer is almost definitely going to have to be such that X and Y are equal to each other. Always true. And we'll see it in the partials as well. So look at the gradient. Excuse me, sorry. The partial with respect to X is 1 times Y. Partial of that with respect to X is 0. Partial of that with respect to X is minus 216 X to the negative 7. And down here, we're going to get the same equation, except X and Y are going to be switched. So instead of Y minus 216 X to the negative 2nd, we're going to get X minus 216 Y to the negative 2nd. Let's check. Partial with respect to Y, Derivative of this with respect to y is x times 1. Derivative of this with respect to y is minus 216 y to the negative second. Derivative of this with respect to y is 0. Now here's the hard part. We're trying to solve this equation, but we don't get any nice numbers right from the beginning. So if I take each of these, right, if I said, I'm going to rewrite this a little bit, I'm going to write it as y minus 216 over x squared equals 0, and x minus 216 over y squared equals 0. So here's the thing. If something is a solution here, it also has to be a solution here, which means x and y have to be the same. So if the solution here and you interchange where x and y are, it still needs to be a solution there. It's technically possible to have a solution that would work for both, that wouldn't be the same, but it's very, very unlikely. So now here's the hard part. Here's what I really don't want to do. I don't want to write y equals 216 over x squared and then plug that in here. We totally could, and it would totally work, and it's totally unfun to do. I mean, it could be not. So, I mean, fine, I'll write it out and you'll see. So I'm going to get x minus 216 over 216 over x squared squared. Multiply, right? Multiply, flip and multiply. So x minus 216 times x squared squared is x to the fourth over 216 squared. Cancel one of those equal to 0. And then you could multiply everything by 216. So 216x minus x to the fourth equals 0. And then you can factor out an x. So you get x times 216 minus x cubed equals 0. And then x is either 0, which we know is not the right answer, or the cube root of 216, which is 6. But there's a better way. So you get x equal to 6, and you plug that back in, and 216 divided by 6 squared is also 6. Well, I don't know if it's a better way, but there's a slicker way. So here's the thing. If you've got these equations, specifically if you see that x and y are, the equations are symmetric, meaning if you interchange x and y, they look the same. If you notice that, you are sure that x has to equal y, but you need to show that before you can actually say it. It would be great if I could say, oh, x equals y and solve this for x and be done, but I can't. But I can do this. I can say, well, I'm going to write y equals 216. Wow. Am I? I'm going to write y equals 12. Okay. Y equals 216 over x squared, and x equals 216 over y squared. And then I multiply both sides by the xy squared. So I get, x squared y equals 216, and xy squared equals 216. Now, they're equal to the same thing. So if these are equal to 216, they have to equal each other. And then x squared y has to equal xy squared. I can divide both sides by x. I can divide both sides by y. Oh, x does have to equal y. So then instead of doing this terrible thing over here, which wasn't so terrible here, but is exceptionally terrible in the next question, and this is why we're talking about this here. Instead, you can say, well, I'm just going to plug in y equal to x, and then this equation becomes x equal, let's do it right here. This equation becomes x equal to 216 over x squared, and then multiply both sides of x squared, and you get x cubed equal to 216. So x equals 6. And then y equals 6. Okay. The last part of this problem, so I was supposed to be more specific, right? The question asks you for the minimum surface area. Technically, you should check to see that it's a minimum, although you don't actually have to do that for this problem. Right? If you're only getting one critical value, it's going to be the thing they're asking for. You could check to see that it's going to give you a minimum. The way we would do that would be to find D, right? So this one, I guess my first parcel is over here. Okay, sorry. So we had that fx was y minus 216 x to the negative second. Fy was x minus 216 y to the negative second. Fxx is going to be see, positive 432 x to the negative third. Fyy should be the same, except with y. And the mixed partial fxy should be 1. All right. So we need to calculate d and then plug in the critical point, which is 6, 6. So then plugging that in, we're going to get d equal to, and let me just plug, so let me tell you, 6 to the negative third is 216 to the negative first, or 1 over 216. So 432 times 6 to the negative third is going to be 432 times 1 over 216, which is going to be 2. So you need 2 times another 2 when you plug in the 0.66 minus 1 squared. It's definitely positive, and since my second partials are both positive, it's concave up, so it's a minimum. And then to find the actual surface area, you would plug in 6 for x and 6 for y. So you get 36 plus, this would also be 36, this would also be 36. So your total volume would coincidentally, and it is a coincidence, be the same as the surface area, which is 100 meters. Doesn't usually work out that way, but 6s are kind of special, so it does work out that way. But it really is just a coincidence. It's because there's a 2 and a 3 and 6, yeah. Anyway, questions about any of this before we move on to the other one, which is worse, but also doable once we know how to do it. Questions? I don't hear any questions, so I'm going to move on. Do pipe up if you have questions. So we'll do this other one, and then we will talk about maximizing and minimizing stuff on a closed boundary. So let's look at the other one, which you want to find the maximum volume, so max volume of a, what have I got here? Of an open box with surface area equal to, I wonder where they're getting that number from. To me, it looks like 3 times a cubic number. That's my guess. I'm just going to use the number they gave me. No problem. Lucky you. Lucky you. So, sorry, my pens are all really dying. I know I've said that before, but they're like really, really dying now. So same idea. We're going to draw the box. And the surface area and the volume equations are still the same. And we still have surface area equal to xy plus 2xz plus 2yz. And the volume equation is still xyz. The difference here, of course, is that now we know that the surface area is equal to a number, and we have to figure out what the volume is. And this is where things get a lot worse. So I'm going to isolate z typically here. Isolating z, I'm going to get z times 2x plus 2y equal to 192 minus xy. I subtracted this and factored out the 2. I should have factored out the 2 as well. Hold on. So then z happens to equal 192 minus xy divided by 2 times x plus y. And that seems pretty terrible. So now let's write our volume equation. So volume is x times y times this heinous trash over here. Same process, just worse functions. So let's take the partial law. The partial, oof. Okay, so here's what I would suggest doing. I would suggest rewriting this as 1/2 times, yeah, really? I think I'm going to distribute, yeah, dude. Sorry, I'm a little, I know I did this problem with someone else one time, and I feel like it wasn't quite as, no, I guess it's going to be really, really gross. So I'm going to write that as, yeah, I'm going to distribute the xy. So I'm going to have 192 xy minus x squared y squared over x plus y. Yeah, fun times. Let's go ahead and find the, so now here's what I'm going to say to make our lives a tiny bit easier. We can see that this is symmetric in x and y, meaning if you interchange x and y, this equation still looks the same. That means when we take the partials with respect to x and the partial with respect to y will look the same, except x and y will be interchanged. which will make our lives a tiny bit easier. So I guess we can do this one here. So let's see. So the partial derivative of x is going to be 1/2 times okay, guys, I got to use the quotient rule. So it's going to be the bottom x plus y times the derivative of the top with respect to x. It's going to be 192y minus 2xy squared divided by, minus, now we flip it, right? Bottom to top minus the top, 192xy minus x squared y squared times the derivative of the bottom, which is 1. Whew, all over the bottom squared.
I have a question.
Yeah.
Could you also rewrite this as the same expression, but x plus y to the power of -1, and then use
I was considering doing it that way, but I decided not to. But I feel like maybe that was the wrong choice.
Okay.
But yes, let's go ahead and So that's what we've got. And that's supposed to equal 0, right? Okay. Let's see if I should have just written it on this side. Sorry. The limitations of board space. So let's see. Here's what we've got. We've got, I think that's still going to be what I want. So let me just contemplate for a second here. No, I think this is what I want. Oh, yeah, that's terrible. I'm trying to think of Ethan's suggestion is maybe what we should do. If you divide each thing by that, you could just write it that way. I'm going to write it this way. So dividing this by this, you're going to have an x plus y to the negative first. So you're going to have vx equal to, sorry, I know this is kind of terrible, 192y minus 2xy squared times x plus y to the negative first, right? That's this divided by this. And then you have this times x plus y to the negative second. 192xy minus x squared y squared. Times x plus y to the negative second. Equal to 0. I don't like that. Here's what I would do instead. Do this. Okay, and then we also know that we have the same equation. So here's what I know automatically Vy looks like. Vy is going to be 192x minus 2yx squared over x plus y minus 192xy minus x squared y squared over x plus y squared. Okay. So here's what I think I did last time. Wow, this is really, really gross. What you can do is you can essentially say, well, look, this is the same as that. Right? They're literally the same. I know I didn't show the work for Vy. Trust me, that is what Vy is equal to. Those are the same, which means these have to be the same. Yeah. So basically, add this over here. So here's the real slick way of doing it. Those are equal. Those are the same, which means these have to equal each other. So now, look at what I've got. 192y minus 2xy squared over x plus y equals 192x minus 2yx squared over x plus y. Then multiply both sides by x plus y. I think you can factor out a y from the left. 192 minus 2xy. Factor out an x from the right. Divide both sides by the same thing. So what that means is now we can go back to our original terrible equation, this equal to 0, and substitute in x for y. I know it doesn't seem like all that great, but I tried to do this one a different way where you actually like solve one of them for y and plug in with the other. It's super incredibly disgusting. So if we plug in x for y or y for x, vx is now going to be 1/2 times, let's see what we get here. I'm going to get a 2, maybe I should look at this one instead. Oh, fine, let's look at this one. I'm going to have 1/2 times a 2x times 192 minus, sorry, 192x minus 2x cubed minus 192x squared minus x to the 4th, all over 2x squared. It looks still pretty terrible, but it's manageable. This is 1/2 times, I don't really care about the right, I'm saying it's equal to 0. I don't care about the 1/2, all those have to 2. And then we're going to get, let's see. Yeah, 2x on it, so 384x squared minus 4x to the 4th minus 192x squared plus x to the 4th all over 4x squared. You can cancel an x. You can cancel 2 x's. 384 divided by 4 is going to be, well, in fact, 384 minus 192 is 192. Divide that by 4, you're going to get 48. And then you got a minus 4x squared plus x squared, so a minus 3x squared over 4, right? Because that doesn't divide by 4 nicely. It works. Yeah, it works. You get 48 equals 3x squared over 4. Multiply by 4/3. 48 divided by 3 is 16. 16 times 4 is 64. You get x equal to 8. Holy smokes, that's not an easy problem. Okay, so here's what I want to say about this. I'm not going to, so I'm done with this problem. I know there's a little bit more to do, like you should find the volume or whatever. But once you know x, then you know y, then you can find z, and then find the volume. But what I want to say for these problems where you notice, and you should pay attention to this, if you notice that the equation for your volume, once you write it in terms of x and y, if you notice that it's symmetric, meaning you can interchange x and y and get the same function. If you notice that, then it's almost always the case that x and y have to equal each other. It's not fun. This problem is really, really gross, but that's kind of, I mean, it's kind of a shortcut, I guess. I'm obviously trying to show the work still, so I'm trying to get to the place where I'm actually like, oh yeah, y does in fact have to equal x. But you kind of can assume pretty safely that if the equation is symmetric, again, that means you can interchange x and y and it still looks the same, then it's pretty safe to assume that y and x have to equal each other. Which is nice. It's also definitely true that when you're finding the partials, if it is, again, symmetric, once you find the first partial, the other partial, and in fact, this isn't what this, so I should no longer be writing this here because I did a whole bunch of manipulations, so that's not really true. But if you, once you find the first partial, the other partials are going to be the same except interchange x and y. Actually, Zach, so I would disagree. The square is not the most optimized shape. It's the most optimized quadrilateral. But it's more because of the symmetry of our first equation, really, right? In this first equation where I know it's erased now, where we're finding the surface area and the volume equation, when you solve for z, you get z equal to, I forget what we had exactly. We had something like z equal to 1/2 x y. I don't remember what it was, but it was it was symmetric. I don't think that's exactly why, but it probably has something to do with it. Okay, let's go ahead and talk about maximizing functions on a closed boundary. So let's look at, let's see, I know I've got some examples up here. Where'd you go? Sure. So let's look at this. It's not the first example I really want to start with. No, that's not. This is okay. Yeah, I was way ahead of myself here. So let's say I want to find the absolute max and minimum of this function, f of x, y, equal to x squared plus y, x squared plus y squared plus x squared y plus 4 on the region described by, there's various ways of writing it, the set containing the points x, y, such that x is between -1 and 1, and y is also between -1 and 1. So basically a square of length, side length 2. So 1. So I'm looking at this entire region. And very similar to how this worked in 17a. In fact, let's do a quick 17a example. I'm going to come back to this, but let me point out. If I said I wanted to find the absolute maximum / minimum of f of x, y equal to f of x, y, sorry, f of x equal to x cubed minus 6x squared on the interval from -1 to 7. Well, what we would do back then is we'd find the critical values. We're going to do that here too. Set the derivative equal to 0, factor out of 3x, you're left with x minus 4. So your critical values are x equal to 0 and x equal to 4. Then we also have to check the endpoints because the function might be the biggest or the smallest there as well. So we have to check f of 0, f of 4, f of -1, and f of 7. And let's see what we get. So if I factor this to make it a little bit easier, f of x is x squared times x minus 6. If I plug in, sorry, one second. I've made the mistake of covering up the chat. I don't think anyone's written anything, but it's always good to be double checking the chat. Okay, so f of 0 is going to be 0. F of 4 is going to be 16 times -2, which is -32. F of -1 is going to be 1 times -7. And f of 7 is going to be 49 times 1. So we clearly have an absolute maximum value of the biggest thing, which is 49, at the point x equal to 7, or x equal to 7. And we have an absolute minimum of, what's the smallest thing, -32 at x equal to 4. So that's the basic idea, right? You're checking the boundary, you're checking the critical values, and you're seeing which of those gives you the biggest thing the function can be and which of those gives you the smallest thing the function can be. So I kind of want to show you, so I'm going to show you this picture instead of trying to draw it for you, because I think these pictures are done really well. So let's look at these pictures before we get going. And I'll read the stuff to you, although I think you can also read. So let me share my, where did it go? The thing I wanted to share. Do that. Okay. So looking at this thing here. So imagine a room where R or D is the floor and f of x, y is the ceiling. And x equals ±1, y equals ±1 are the walls where could the highest and lowest points of the ceiling occur. So you could have a ceiling like this, where the highest point is just some point in the middle, vaulted ceiling. And the minimum points, right, are actually every point along the boundary would be a minimum. So you can have more than one. You can actually have an infinite number of minimums. But you could also have something, you could have a roof that looked kind of like this, right? Where the maximum points are actually all the points on this line here, and the minimum values are all the values or points on this line over here. And then if you had something that looked kind of like a saddle, you would say, okay, it looks like the maximum is occurring right over here, and the minimum is occurring right over here at this on this wall. So basically the idea is the max and the min can either occur at some critical point in the middle of your region, at some corner. Oh, I think this one was meant to be drawn so that this side's actually higher than this side. Yeah, see, if you look at this right-hand face here, it's, yeah, sorry about that. So, right, so really only this point's the highest and this point's the lowest. So you could have a max or min at a corner, or you could have a max or min at some middle point, doesn't have to actually be the middle, some in-between point of a corner along one of the walls, where you have a critical, you find like a critical point on the wall, which we'll talk about. So we're going to check for extrema at all three of those types of places. So let's take a look here. Let me actually do one thing real quick. Let me just do that. Sure. Great. Gotcha. All right. So let's look at this first one. So we're going to check, again, all three categories of things. We're going to check the corners. So we're definitely going to check the function at 1, 1, -1, -1, -1, -1, and -1, 1. But then we also have to check at along the walls. So this wall is the wall y equal to 1. This wall is x equal to 1. This is y equal to 1. This is x equal to 1. And then any critical points we find that are in the region itself. So let's go ahead and find the critical points. So we're going to find the gradient, as we usually do, set it equal to 0. And that's going to end up giving us, what do we get here? So my gradient's going to be, my chair is really in the way today. So let's see, partial respect to x is going to be 2x plus 2xy. Not 2yx would also be fine. And the partial respect to y is going to be 2y plus x squared. Again, we've talked about this a little bit. If I have a choice to try and figure out kind of what my critical points are, I'm going to always deal with the equation that looks like it's a little easier. So I'm going to deal with this first equation. So setting 2x plus 2xy equal to 0, I can factor out the 2x. So I either get x equal to 0 or y equal to -1. And then I plug those into the other one. So then 2y plus x squared equal to 0. If x is 0, well, then I get 2y equal to 0, which gives me y equal to 0. So I get the critical point 0, 0. And if y equals -1, let's do that one down here, I get -2 plus x squared equal to 0. I get x squared equal to 2. I get x equal to plus or minus the square root of 2. So I get the critical point y equal to -1, x equal to plus or minus root 2. Now, here's something worth observing, really worth observing. That point isn't in our region. If x is root 2 is like, I don't know, right about there. So x equal to root 2 and y equal to -1 would be like down here, which is outside the region. So we don't want to test points that are outside the region, whether or not they're right. Kind of like, right, for this example, if I had found a critical point that was outside of the interval -1 to 7, I wouldn't test that point either. So great, we really only have one critical point that we have to check. So here's the list of things that we have to check. We have to check f of 0, 0. Oh, we're not, I've gotten a little bit ahead of myself, actually. We need to look at the walls as well. So let's check the walls next. I have to be a little bit careful here. Yeah, okay, so yeah, let's check the walls. So we have to look for critical points along the walls. So again, here's our function, f of x, y equal to x squared plus y squared plus x squared y plus 4. So let's look at the wall x equal to 1. I'm going to plug in 1 for x. So f of 1 comma y equals 1 plus y squared plus y plus 4. And then I'm going to find the derivative of that with respect to y. Fy of 1 comma y is going to equal 2y plus 1. Set that equal to 0. And you get the critical point where, let's see, y is going to equal negative 1/2. So on that wall, x is 1, y is negative 1/2. So there's another point we have to check. When x is 1 and y is negative 1/2. Okay, now let's do it for y equal to negative 1. Sorry, for x equal to negative 1. It's actually going to give you the same result. Whereas x equals negative 1, since x is squared, f of negative 1 y is also going to be 1 plus y squared plus y plus 4. So you're going to get x equal to, so you're going to get the point negative 1 comma negative 1/2. Do you guys see why that's the case? Right? I get the same equation, I get the same y value, but I've got now x equal to negative 1. So that's going to be this point over here. And then finally, setting y equal to something. If y equals, well, not just something, y equal to one of the walls. My walls are y equals 1, y equals negative 1, x equals 1, x equals negative 1. Good job. Okay, so setting y equal to 1, we're going to get, let's see, f of x comma 1 equal to x squared plus 1 plus x squared plus 4, which is 2x squared plus 5. And if we take the derivative of that, we're going to get 4x, and set that equal to 0, we're going to get x equal to 0. So you get the critical point 0, 1. And if y equals negative 1, we'll probably get something. Oh, no, I don't think we actually get the same thing. Y equals negative 1, I think it's kind of wonky. F of x comma negative 1 is going to be, let's see. Sorry, x squared plus 1 minus x squared plus 4. So that's going to be 5. So here's what that's telling me. Along the wall y equal to negative 1, the function is a constant value. Meaning there isn't going to be a max or a min there unless they happen to all be a max or a min. So whatever, but that means we could just check a corner, right? So along the wall y equal to 1, we have the point 0, 1. And along the wall y equal to negative 1, the function is the same value there no matter what you pick. In fact, right, we know that it's equal to 5. Right? It's equal to 5. So we know that all along this line here, including the endpoints, the function value is 5. Interesting. Okay, so now we have to check all of these points. All of the corners, all of the critical points on the walls, and any points in the middle. I'm going to erase this work here so we have some room. We're going to try and do this relatively quickly. So let's see. So f of 0, 0 is going to be 0 plus 0 plus 0 plus 4. F of 1, 1 is going to be 1 plus 1 plus 1 plus 4. F of negative 1, 1 is going to be, okay, be a little bit careful, 1 plus 1 plus 1 plus 4 still. I don't really need to check these corners down here because we already saw that they were 5. You could, right? We know that f of 1 comma negative 1 is 5, right? 1 plus 1 minus 1 plus 4 is going to be 5. And the same deal for negative 1. Okay, let's see. I've got these points left to check, which this was 0, 1. This was 1 comma negative 1/2. This was negative 1, negative 1/2. So plugging in 0, 1, f of 0, 1 is going to be 0 plus 1 plus 0 plus 1, 4. Okay. So interesting, right? So right here it's the value of 7, and here the value is 1. So this one probably looks something like right, like that over there at the end. It's kind of like that, right? Like here it's 7, here it's 7, here it's 5. And 0, 0, it's 4, so it's even kind of lower down there. I know my picture is not good. Don't judge me, please. Okay. And then checking these points, f of 1 comma negative 1/2 is going to be, let's see, 1, I have to write this out, 1 plus 1/4 plus 1 times negative 1/2, so minus 1/2 plus 4. So that's going to be 5 minus 1/2 is 4.5, plus the 4th is 4 3/4. So that's 4 plus 3/4. And then plugging in 1 comma, sorry, negative 1 comma, negative 1/2. I think we're going to get the same thing. So we're still going to get 1 plus 1/4 plus 1 times negative 1/2 plus 4. That's the same thing. Okay, so now we just have to ask ourselves which one's the biggest. Those look like they're the biggest. Which one's the smallest? That one. So we have an absolute maximum, that's an absolute minimum. So be careful. The questions I think usually ask for the minimum value and where it is. So it's a minimum value of 4 at the point 0, 0. And we have an absolute maximum value of 7 at both the points 1, 1 and negative 1, 1. So it's definitely possible to have an absolute maximum for more than 1 point. Same for an absolute minimum. All right. Let's squeeze in one more. Definitely have time for one more. So the thing is not always going to be a square. Squares are kind of the nicest to deal with, but they're not always what you get. Let me look at this one before I start. Is this stuff a little too easy? This one's a little too easy, but fine. We can do this one, and then next time we'll do a harder triangle one. So let's look at this function. Let's say our function f of x, y is equal to 1 plus 4x minus 5y. And the region is the region bounded by the triangle with corners 0, 3, 0, 0, and 2, 0. It definitely is going to be in your interest to draw these regions. So here's our region. I got 0, 0. I got 2, 0, and I got 1, 2, 3, 0. I'm looking at that. So we know we're going to have to check the corners. We're going to check any critical points and any points in words. Any points where you have a critical point along one of the walls. So let's see. So taking the gradient, you get fx is 4, fy is negative 5, and that is never going to equal 0, 0. So you have no critical points, which is not surprising because this is actually the equation of a plane, and the plane just kind of like keeps going up. So there isn't really any part where it kind of goes up and then goes down. Similarly, if we look along any of the walls, we're not going to have that either, right? So along y equal to 0, we're going to have the equation f of x comma 0 equal to 1 plus 4x, which again doesn't have any critical point. If you take this derivative, it's 4. Along x equal to 0, we have f of 0y equal to 1 minus 5y, which again doesn't have any critical points. And finally, along this line, which we need to find the equation of, okay, this line, the slope is, I go over 2 and down 3. So the rise is negative 3. The run is down is over 2. And then my y-intercept is 3. Right, along that line, So this is where it gets a little bit tricky. So you have to actually take your equation and plug this in for, sorry, I was saying this, my y equals that. To plug this in for y. So we have our equation 1 plus 4x minus 5 times negative 3 halves x plus 3. But I think you can both all see that since this is x to the first, the derivative is still just going to be a constant. The derivative here is 0 plus 4. Well, that's 15 halves times x, so plus 15 halves plus 0. Oh, there's no critical points. So in this one, you only have to check the corners. So f of 0, 0 is 1. F of 0, 3 is 1 minus 15, which is negative 14. And f of 2, 0 is 8. So an absolute maximum of 8 at the point 2, 0, an absolute minimum of negative 14 at the point 0, 3. We want to do one more, but I feel like that would be irresponsible because there's not that much time left. Let me just do part of one more. So I just want to show you another triangular one, and we'll probably finish this one up on Wednesday, or we can do it office hours if you want to find office hours. But here's another one. So let's look at this function. F of xy equal to 3 plus xy minus x minus 2y on this triangle. The triangle with corners at 0, 5 and 5, 0 and 0, 0. Okay, specifically, so we could find the critical values. I will tell you the critical point is the point 2, 1. So right here, right here. So there's your critical point in the region. And then you're going to test the corners. But what I really want to talk about is testing the walls. So the walls are kind of the hardest part. So the walls. So we've got the wall y equal to 0. So y equal to 0, I'm going to do f of x comma 0. I'm going to plug in 0 for y, so I get 3 plus 3 minus x. And then the derivative of that is just negative 1. So we get no critical points along the wall y equal to 0. Along x equal to 0, f of 0y is equal to, let's see, 3 plus 0 minus 2y. Again, not very interesting. Fy is going to be negative 2, which isn't 0. So no critical points along the walls. So you get no critical points on your walls, and you're checking the corners. But the third wall, this is the equation. Let's see. This is y equal to negative x plus 5. So I'm going to plug that in for each of my y's. That's where things get interesting. So usually the one that's kind of slanty, or ones that are slanty, those are the ones that take a little bit more effort. So if we look at y equal to negative x plus 5, I plug that in here, I get my function now of x is going to be 3 plus x times negative x plus 5 minus x minus 2 times negative x plus 5. Let's multiply it out. 3 minus x squared plus 5x minus x plus 2x minus 10. Let's simplify that a little bit more. I get negative x squared. I get plus 5x minus x is 4x plus 2x is 6x. And I get 3 minus 10, which is minus 7. And then my derivative there, f prime of x, is negative 2x plus 6. At that equal to 0, you get x equal to 3. And then y is negative 3 plus 5, which is negative 2. Sorry, negative 3 plus 5, which is positive 2. So we get the point on the line 3, 2. So here are the points we have to check. The critical point in the region that we didn't find together, but I told you was 2, 1. All these corners, you always have to check the corners, and then this point on the wall that might be a max or a min. All right.